Remember when we modeled free fall motion and we ignored air resistance? Well, you've probably come to realize by now that you can't get away with that in most practical problems. Think about skydiving. A parachute without air resistance isn't much of a parachute at all. Fortunately, with the new version of our code that animates motion based on forces, we can study falling with air resistance. We usually refer to the force of air resistance as the drag force, since gravity is trying to drag our parachuter through the air. The drag force arises from the skydiver colliding with the atoms and molecules in the air. Each nanoscopic collision robs the skydiver of a small amount of kinetic energy. The effect of these collisions adds up as the skydiver falls through the air, and the faster the skydiver moves through the air, the greater the drag force. The simplest version of the drag force has three pieces: a negative sign indicating that the drag always points opposite of the skydiver's velocity, a constant called the drag coefficient, which gives an idea of how rough the collisions are between the skydiver and the air, and the velocity of the skydiver. There are more complicated versions of this equation that you'll get to explore in the activities linked to in the description below. This relationship between drag force and velocity is why physics teachers usually don't solve this problem on the board, because having force depend on velocity and velocity depend on force requires calculus. However, our code can handle this interdependence just fine. First, we calculate the weight vector pulling down on the skydiver, just like we've done several times now. Next, we set the drag coefficient. Just remember that the higher this number is, the stronger the drag force will be. Then, we set up the drag force vector. Since this force points opposite of the skydiver's velocity, we simply multiply each component of the velocity vector by a negative sign and the drag coefficient. This construction ensures that the drag force always points against the velocity. Since this velocity vector updates with each pass of the loop, the drag force will also update with each pass of the loop. When we run the code, we initially see the skydiver accelerating downward as we did before, but as the skydiver's speed increases, so does the magnitude of the drag force. Notice how even though the weight vector remains constant, the magnitude of the drag force increases. This increase causes the net force on the skydiver to change from a strong negative value to a weaker negative value as the two forces come closer to canceling. In fact, if we increase the drag coefficient to a value of 4, we can quickly see the drag force increase to a magnitude nearly equal to the weight. The net force becomes very close to 0, which makes the velocity level out toward a constant final value. We call this final value the terminal speed. In this case, the skydiver's terminal speed is about 2.5. Terminal speed is an important concept in aerodynamics and depends on the drag coefficient and the weight of the skydiver. We can also use this code to study projectile motion with air resistance. We just need to give our initial velocity two positive components, and we can watch our projectile fly through the air while being impeded by drag. Notice how lopsided the trajectory becomes, since the drag force acts in a different direction in each frame of the animation. If we look at the motion graphs, we can see the vertical component of the projectile's velocity approach a terminal speed like we saw before. On the other hand, the horizontal component of the projectile's velocity approaches a terminal speed of exactly 0 since there's no force pushing it in the forward direction. These results are really interesting, and there are many possible outcomes for you to explore, but you can probably see now why most physics classes don't include this complicated force in their studies. Click the link in the description below to find a set of activities that will help you learn more about the drag force, including variations in how the drag force is calculated.